You did D? You didn't read directions?
I read them later, but I was already committed to doing D.
Oh, 824B as in boy. So I had a shape that looked something like this. Now on this one, let's see, what do we do on this one? Yeah, we had to do the whole thing, didn't we? Down, get the polar moment of inertia. So I broke this out basically like that was a section and that was a section. So this was number 1. This was number 2. And this was number 3. So area for 1 and 3 are the same. And that's 5 times 1. 5 square inches. Area 2 was 8, or 1 times 8, base times the height, right? 8 square inches. Let's see. Y bar is simply 5 inches. This is 1 inch, that's 8 inches, that's another inch, that's 10 inches high, right? So the center of gravity is going to be right in the center of that thing. And for that matter, the X bar is going to be 4.5, isn't it? And that's, you've got what, 5 inches here, 5 inches there, 5, and this is 1 inch, so half of this is a ½ inch, so 5 inches minus a half puts you at 4.5. Okay, so that makes it, it's somewhat symmetrical, isn't it, for that matter. Let's see, D1 and D3. So to get this distance right here, there's a center of gravity for each of these, right? The distance from here to there that's going to be, we said this was 5 inches, right? 5 inches, we said this was a ½ inch, so 5 minus a half is 4.5, isn't it? And that's for both of those. Okay. Eventually we're going to need the same thing for the x's, aren't we? The x bar. Okay, so, but I like to stay with one thing here first. So the moment of inertia about the x-axis for 1, and that'll be the same for 3, is the base, which was 5, times the height cubed divided by 12, right? Oh, let's see. I got a little bit more to do there. There's a D value in there. There's a D value, so anytime there's a D value, we have to add the area, which is 5 square inches, times the D, which was 4.5, and that value has to be squared. So it's the moment of inertia about the shape plus the area times the distance squared. That should turn out to be something like 101.7 inches to the 4th. So that's the two wing pieces, if you will. The moment of inertia for the second piece about the x-axis is going to be 1, which is the base, times the height, which is 8 cubed divided by 12. There is no D value because the center of gravity of part number 2 is exactly the same as the center of gravity of the total piece, isn't it? So 5, what was it, 5? It'd be 5 minus 5, basically. 1 plus 4.5, or 1 plus 4, excuse me. So there is no D value, so that's all you have there. That turns out to be 42.7 inches to the fourth. Our total then, stop me any time now if you got a question. Total about the x-axis is just those two, isn't it? It's 2 times the 101.7, which was the moment of inertia of each of those two pieces. But this was just for one, right? And then you had to multiply it by 2.
No, I was forgetting to do that.
Plus, yeah, you don't want to forget to do that on the test. The other one for the x2 was 42.7. So you should end up with something like 246 inches to the fourth.
So you could have, that's kind of, like earlier when you were doing IX1 and IX3, you could have left out the area and the distance squared and just found the moment of inertia of those parts and then put that in down at the bottom when you did the total, right? Is that kind of how you?
No. No, I don't. So what you're saying is just take this value right here, multiply it times 2?
No. I was just saying, no, I was just saying, if you just found it for each part, skip the 5 times 4.5 squared, and then you could put that back in, the 5 times 4.5 squared back in down at the bottom when you did the
You'd have to multiply it times 2, though.
Right.
Yeah.
I know.
Yeah.
I was just saying that's.
You could take this whole thing and multiply it times 2, right?
Yeah.
You'd have to take this whole thing and put that in brackets times 2.
Right. That's
Yeah.
not what I was talking. I wasn't talking about the times 2 part. It's all right. I got it. Just trying to clarify.
Well, I hope that was enough. I mean, because you have to have this whole thing to be the moment of inertia for one of them.
Right. Relative to the axis for the whole thing.
Right.
But if you just did it for the part itself, then you could put that back in down at the bottom. I guess that's just how I was thinking about it, and it's the same thing, just doing it in a different place.
Yeah. Yeah. Exactly. Yeah.
Well,
You
add
could
'em all up.
you could take 2 times this and then 2 times that, as long as you do 2 times on both of them.
You can add them together up top or add them all together down at the bottom. As long as
Yeah.
you account for everything.
But realize this whole equation here is the moment of inertia for this square relative to the center of gravity for the whole thing. You have to have the area times the distance squared for that transfer formula.
Yeah.
Okay. Anything else? So that takes care of the moment of inertia about the x-axis. But since we're dealing with the polar moment of inertia, we have to find the moment of inertia about the y-axis, don't we? Okay, well, we already said that x bar is 4.5. Okay, so let me redraw the sketch down here, maybe will help. So let's redraw the sketch. Not to scale, again. Okay, so now we're dealing with this axis right here, aren't we? The YY. So now we're going to have a center of gravity here and a center of gravity here. And our D values are going to be here now, aren't they? This was 1, wasn't it? Yeah, 1. And then D3 will be right here. Of course, D2 there won't be any, will there? Be 0. Yep. So now what we do? Well, let's see. So we can do D2 equals D3 equals So let's see, what's that gonna be? Well, and again, this,
D1 or D2?
oh, sorry. Thank
I
you.
was like, we just said that D2.
I'm getting old, can I say? But I won't tell you that I did that on purpose to check on you, okay? Yeah, I'm not gonna pull that crap. You know better. So, I wrote it here and then just
Yeah.
didn't carry through. So that total distance was 5, wasn't it? And this is going to be a half. So if the total distance was 5, that means the distance from here out to the end was 2.5, right? Need to get some more paper up here. So let's do this right. So the distance from here all the way to the end is 2.5. The distance from this edge, or from this end right here to this half, is a 1/2 inch, isn't it? So the distance here would be a 1/2 inch. So that means D2 and D3 are going to be 2, aren't they? The difference from the center of gravity of this piece to the center of gravity of that piece, the distance between those two is going to be 2 inches. Copy that? Okay. Then what do we have to have? Excuse me. We had the areas, right? The area of 1 equals the area of 3 equals, what was it, 5 square inches. We had the area of 2, which was 8 square inches. We said X bar was 4.5 inches. So, and we said that D1 equal, yeah, I'm not going to rewrite that. We've got it there. D1 and D2 equals 2 inches. D1 and D3. D2 equals 0. Okay, because it's right through the axis. What else do we need? Need the y bars, or the moment of inertia of each one, don't we? Moment of inertia of 1 and 3 equals what? The 1, which is the base, or excuse me, the height. 1 is the height times the base, which is 5 cubed divided by 12. Right? We reverse those, the 5 and the 1. And of course I probably screwed up again, didn't I? Yep. I don't really want the equal sign in there just yet, because I do have a D value for those, don't I? Plus the area, which is 5, times 2, which is D squared. So each one of those is that value right there, which turns out to be 30.4 inches to the 4th. Moment of inertia about the y-axis for number 2, middle one there. The height is 8 times 1 is the base, cubed divided by 12. There is no D value, so we're good putting the equal sign on this one. 0.67 inches to the 4th. Now, look at that. Does that make sense? It's saying that this piece is stronger than that piece, isn't it? It's saying that this little short piece right here is stronger than that big piece right there, isn't it? It does make sense because our force is going this way now. It's going on the x-axis. It's parallel to the x-axis. We're doing the y, right? So the force is going parallel to that x-axis. So yeah, this can withstand more than this big piece that's going to want to bow, isn't it? This one is much stiffer. If I turned this whole thing 90 degrees and you were pushing down on it, you'd say that was stiffer, wouldn't you? Than that 2x4 that's laid out the long way. In this case, 1x8. But remember, we're looking at the y-axis now, so the force is going parallel to the ground as opposed to perpendicular to the ground. So it has to make sense when you look at it. It's like, wait a minute, that number's kind of crazy. But it's really not when you look at it. Hey, I'm looking at it from a different perspective. Okay? So then to find the total, we just add those two up. 30.4. Actually, that's times 2, isn't it? Plus 0.67. When you punch those in, you should get something like 61.5 inches to the fourth. And again, that number is quite a bit smaller than the 246 number, isn't it? Because of how you're loading it. Now the J part's easy. The polar moment of inertia, 246 inches to the fourth plus 61.5 inches to the fourth equals 307.5 inches to the fourth. And what did we say the polar moment of inertia was used for? Twisting, right? Torsional type. So you are combining both of those to make sure this thing won't twist. You're allowed to do that, right? I mean, if you, in reality, if you had something twisting your arm, you know, you'd be resisting it in two different axes. So that's what you're doing there, isn't it? You're combining that. So later on, hopefully, if we get time, we'll talk about combined stresses. And that's where this will come into play. There's a lot of times I've never actually talked about the polar moment of inertia at this point. I waited till later. But since the book, I had to look at that the other day. It's like, yeah, do I want to talk about this now or later? But since the book brings it up now, I figured that was the best time to do it. Okay, because you really won't use it till towards the end. Questions? What really scares me is you don't have any questions because you didn't practice. But we'll find out Friday, I guess. And I think you know by now, I know what I'm talking about there. This is our fourth test, right?
So David, when you got the
Oh, sorry.
when you got to the center of the piece on the top there, you said it was 2.5.
Right.
Subtracted the 0.5. Is that from the height?
Okay,
of the piece?
so let me blow that up, if you will. Okay, I'll do a detailed drawing of that because that was kind of crappy. So what it is here's the top piece, and then this piece comes down this way, right?
Right.
Well, that's not very nice. So that piece comes down like that, and let's extend that down a little bit more. Then this comes down like that. Okay, and I'm going to break that off right there. So let's say that's the center of gravity of that vertical piece, okay? And I broke that up like this. So the center of gravity for this piece is right about there. And that value, so what I did was this overall height or overall length of this thing is 5 inches, right? Which means that this distance is 2.5, right? Okay, and then I think I can get that in there. Okay, so then this one, this distance right here is 1/2 inch because this overall distance here was 1 inch. Okay, so this has to be halfway, right? So if we, and let me get this out of here for a second. So that's 1 inch. So if we project this on up, this distance right here, which is, in this case, what was that, was that D1?
Yep.
D1 then equals this 2.5 minus the half, which was this half right here, wasn't it? It's the difference between the center of gravity of 1 and the center of gravity of 2, or yeah, that's 2, of 2. That's what D1 is. Okay?
The center of gravity for 2 is the center of gravity for the whole component.
That's correct. Well, yeah, that's actually the center of gravity of 2 equals y bar, doesn't it?
Right.
Yeah. Or excuse me, x bar. The center of gravity of 2 equals x bar, because this would be yeah, that's right.
I was doing 4.5 minus 2.5. It gave me 2. But I was just looking at it.
Yeah, that would work on this one, but it wouldn't work all the time necessarily. See, you'd have to go, it has to be the difference between x bar, which is actually the center of gravity of 2 in this case, the difference between x bar and x bar is 4.5, isn't it?
Right.
Minus the
Yeah,
2.5.
that's where I got
Yeah.
the 4.5 was
The 4.5 was from this edge here, right?
Yeah.
And it would have been the same for the
That
other.
2.5 is the same.
It would have been the same for the other piece too. But now, if one of those legs was different than the other one, that's where you would have to be careful and make sure you get it from the X bar. Does that help? A little bit.
Yeah, X bar,
I can't do much more than draw you a picture. What?
X bar is CG2, that's,
They're one and the same, aren't they? 4.5 from the y-axis. If we remember, x bar was 4.5, and that's relative to this axis right here, right? If we were doing this y, and this x, the distance from here over to the center of gravity was 4.5. Okay. Anything else on that one? $831, huh? Looks bad, doesn't it? Huh? You couldn't get this one? This one is the easiest one.
Yeah, I don't know about that.
Oh. Hardest part's drawing this one.
So you had to do, well,
So you got those 4 pieces of angle iron and those plate, right? It's as good as it's going to get today. And ever, for that matter. So I made this 1, 2, 3, and 4, and then I made this 5 plate. Okay? So, the area of 1 equals the area of 2 equals the area of 3 equals the area of 4 equals what they told me it was in the book, right? 3.6 square inches. They told me that. Thank goodness. Because it's a piece of angle iron, so you'd have, those little radii on the ends and in the middle. The area of 5, they didn't have to tell me about that. I'm smart enough to figure that out. 24 times 0.375. 9 square inches. D1, 2, 3, and 4 are all the same. Well, first I need to have Y bar, don't I? 24 divided by 12. Or excuse me, divided by 2. Putting my answer in there. 24 divided by 2, right? Equals 12. Hey, are you allowed to laugh?
Yes.
Absolutely. I told you that at the beginning of the semester, right? Inches. Huh. Okay. Let's see. So then D1, 2, 3, and 4. So my center of gravity is right there, isn't it? How do I know that? I know that because this thing's symmetrical, isn't it? I could go in and I could get the center of gravity of this piece and that piece and do all that calculations, but it's symmetrical, so I really know that that is 12 inches. Just like I would know, if I knew the distance from here to here, I would know that the X bar would be, I don't remember what that width is totally, but probably 6, 12 and 3/8 divided by, so it'd be 6 and 3/16, wouldn't it?
Yeah.
Would be the X bar. Okay. So then D1, D2, and all that is going to be, let's see, 12 inches minus, now I got 0.933. Where did I get that number? Out of the book. Back on page. The angle irons, wouldn't it? Somewhere. Did I already go past it? Where was it?
493.
I put down table, but didn't put the page number. I must have fat fingered it and didn't go through it.
493.
493. Now, what you have to be careful of there is the way that thing's oriented. It's a 6 by 4 by 3/8, but you have to make sure. I think the way that the drawing showed it, the 6 inches was on the horizontal axis, right?
Yeah.
So you had to use the X value, right? For a L 6 by 4 by 3/8, and that's 0.933. So we subtract that from the 12, because the 12 is the height, right? Equals 11.067 inches. So that's the distance from here to, let's see. That's interesting. Oh, yeah, that's a 24 length plate, isn't it? It's like, wait a minute, I looked at that 12 and the 12 is halfway. So 12 inches minus, so the 12 inches is the total, minus this 0.933, which is given in the book, which is actually up in here somewhere, isn't it? What?
Area 5.
The area is given. It's in that same chart. 24 times 375. That's just given in the dimensions. Okay, so 11.67. So that's the same whether it's on plate 1, 2, 3, or 4. Some are up and some are down. Doesn't matter. What else do we need then? We need the X moment of inertia for all of those pieces. So the moment of inertia on the x-axis for 1, 2, 3, and 4 individually now, mind you. Okay. Well, actually, I do show it as all 4 of them. Is going to be the moment of inertia of each one, which the 4.86 is given in the book, right? In the chart. That's the IY in the chart, right? Again, you have to watch the way it's oriented. It makes a difference, doesn't it?
Yeah, it'll burn you.
Okay. That plus the area, 3.6, times the distance, which was 11.067, and that number has to be squared, times 4, right? Yep. So the total for all of those is 1780.
Because of there's 4 plates, right?
That's
Yeah.
4
Right.
angles.
Yeah, 4 angles.
4 angles.
Yeah.
1783.13 inches to the 4th. Yeah, so what's in brackets would be each one of them.
Yeah, and then
It's the moment of inertia of the angle plus the area times the distance, the d squared. And then all of that multiplied by 4. Then I have to find the moment of inertia of the plate.
You ever get a D for 5?
It's 0.
Oh.
D5 equals 0 because again the X bar, or excuse me, Y bar for the whole thing is 12, and what would Y bar for this individual piece be? 12. Okay, so 12 minus 12, 0, which makes it nice because then I don't need to worry about that when I do the moment of inertia of this particular piece. It's going to be the base, which is 375, times the height, which is 24, cubed, divided by 12. 432 inches to the 4th. And we just add those up and we get the moment of inertia about the x-axis for the whole system, don't we? 1783.13 plus 432. How about 2215.13 inches to the 4th? And that's the only one you had to do on that one. Moment of inertia about the XX centroidal axis, right? Or the moment of inertia about the centroidal XX axis, which is where that 0.5, that 5 is pointing to actually. Just make sure you get your orientation right. It's the key. I do believe I have a tutoring session coming up if you need help. If not, and I'll go get my calculator and see